Welcome online lecture series in wireless mobile communication. Today our topic is long distance and log normal shadowing. Uh, in previous we have seen free space path loss model, or we have seen the your two rays path loss model. Uh, Actually, these two models are in correct to predict the path loss uh, between the transmitter and the receiver. And this two path loss models, one is the our long distance and another one is the log normal shadowing models, uh, have been removed the previous drawbacks. So let us see. Uh, There's are to remove this uh, you could say the a, drawback from the previous model is having two approaches. First approaches is the your analytical approach, and another one is your the uh, that is empirical approach. So first, your approach is analytical analytical approach, and another one is your empirical approach. So question is, what is the analytical approach and what is the your empirical approach? Empirical approach. As we all know, that the most radio propagations models are derived using the combinations of this analytical approach and the empirical methods. So the empirical approach is based on the fitting the curves or analytical expression that they recreate a set of the measured data. So this has the advantages of implicity, taking into account all the propagations factor, both known and unknown, uh, through the actual field measurements. The validity of an empirical model at the transmission frequencies or the environment are rather than those used to drive the model can only be established by the additional measured data in a new environment at the required transmission frequencies. So over the time, some classical propagations model has emerged and which are now used to predict the large scale coverage for the mobile communications system design by using the path loss model uh, to estimate the received signal level as a function of distance. It becomes possible to predict the signal to noise ratio for a mobile communication system. Using the noise analysis technique, the noise floor can be determined. For example, the two-ray model described for using the estimate capacity in the spectrum cellular system before such system were deployed. The practical path loss estimation techniques is now used in an analytical approach. So the modeling using the mathematical equations and assumptions model assumptions, certain assumptions model upon a propagation mechanism, and it is mathematically derived by the equations to calculate the path loss. That such type of approach is called analytical approach. And in an empirical approach, the model by the physical measurements and the fitting a curve by a considering all known and the unknown parameters collected measurement to fit the some curves by experience says that the empirical approach is not good for the formulating the path loss model. Therefore, we now adopt the analytical approach for driving the path loss model. So you can see there are one side is a huge building, and other side is the like natural mountains. Then the receiving path loss model is not equal by in this environments. So the environments also play a important role to drive the path loss. So in such conditions, you need to calculate or drive the under this specific use environments that play an important role to calculate the received signals by the actual this is conditions when the path loss is not uh, received by this in the same view. So we need this to deal the such types of uh, path loss in an analytical approach. And in previous model, we all know there are the lot of assumptions has been created to made to uh, solve the problems. Such assumptions is impractical, so it is not used for in this scenario. So it is the equally important to validate the model in the various environments. So this is the not use empirical model to calculate. So we are now go we are now uh, go with the analytical approach. So under the various taking the consideration under the various environment, use specific environment with our the required frequency of transmissions. So the model will be validate validate the validate in various use environment environment uh, with with our required frequency. So it is evident that model can be evaluate the our required frequencies of transmission, and then it will be useful. Otherwise, the by the otherwise it is not useful. So it is equally important to path loss evaluate the long distance and the long normal shadowing model. So therefore, therefore it will be evaluate and drive long distance and long normal shadowing. Long normal shadowing. So the path loss model also enable us to predict to calculate the important transmission parameter. So under this under this path loss path loss model model also ensure ensure us to us to predict predict and calculate the important parameters important parameters parameter that is the transmission parameters, that is the that is the transmission parameters parameter such as signal to noise ratio, noise noise floor, and capacity of capacity in in spread spectrum. So it is the pure analytical approach for calculating the path loss model are incorrect because of the many immature assumptions made to reduce the derivations complexity. In the previous previous model, we used the many immature assumptions assumptions made to reduce the derivations complexity. Derivation complexity. So driving the free space model and the two race model is quite a mean of uh, to use the lot of assumptions for getting the required uh, results by the derivation reducing the derivations complexity, so which is not seen in the your this uh, any in practical situations. But still the formulate to made these assumptions to get to get the path loss model either in free space or in the two race model. Therefore the actual um, make more realistic modeling to handle this path loss models. So considering the practical scenario, our approach is to cap all these considerations to modeling this the path loss model. So this is the actual necessity, the modeling of the path loss model. So there is so that why it is the area where we have dealing the long distance and the long normal shadowing in this our approach. So we should need a some practical approach also. So we are dealing the practical practical link budget design design using the path loss model, using path loss model. Long distance and log normal shadow. So now move with practical link budget design using the path loss model. So we will taking the practical link budget design using path loss model. So eliminating the drawback of the previous model, a realistic path loss model can be developed in the two ways. Eliminating the drawback of drawbacks of previous model model a realistic realistic path loss path loss can be or developed developed in two ways. First is long distance path loss model or second is log normal shadowing path loss. So start long distance path loss model. So log distance path loss So when we consider the path loss models formulations so far, it is clearly noted that the received signal power decreases decreases logarithmically. Over a distance. So it is given by path loss PL in decibel dB is equal to 10 log transmit power to the received power, that is equal to minus 10 log. This value is equal to, after the derivations, minus 10 log lambda upon 4 pi d का whole square. So this is what it is, the free space model where path loss is logarithmically 1 by d. And when you consider path loss in 2 days model, that is the tan log transmit power to the received power is equal to tan of log separation distance की power 4 divided by gain of transmitter, gain of receiver, and the product of the height of the antenna, transmitter antenna, and height of the receiver antenna का whole square. This is the 2 days model. And you see here path loss in dB in 2 days model is proportional to the logarithmically log of the separation distance की power 4. So if we want to general path loss equation with respect to the separation distance between transmitter and receiver is can be given by therefore the general path loss equation with respect to separation distance between transmitter. T stand for transmitter, R stand for receiver. Separation separation is given by path loss is separation distance at D bar is directly proportional to the separation distance to the reference distance D naught. A is the power of n, and it implies that path loss at distance D bar is equal to path loss at reference distance D naught bar plus tan log of n log of separation distance to the reference distance due. So this equation where you see this is equations uh, is given by in terms of path loss, where this is the path loss D is equal to separation distance here actual distance actual distance between the transmitter and receiver separation, and 2 naught is reference distance reference distance or you can say closing distance closing distance, and n is the path loss exponent. N is the path loss. So N is the path loss exponent. Path loss exponent. And var of PL is equal to in symbol in symbol average value. Well, in symbol because of the there is a free space and uh, there is a huge environment around the surrounding the transmitter and receiver. It plays the important roles to prevent create this path loss. So under these circumstances, the PL will be calculated either in the free space path loss model or also calculate on the two uh, race equation model. Then this can be tested on the different measurement on environment effect. Under the such environmental effect, that should be kept into the consideration. That's why it is the in symbol average value. These values are taken from free space and the two race model are totally not matched together. They are different. One is the inversely logarithmic of the distance, other is the directly proportional of the distance of the power 4. So this is the uh, not equal. So we will be dependent on the practical scenario to test other experimental data and to analyze and fed into the computer program software, and then after the estimation of the difference uh, uh, um, uh, scenario, then we calculate the uh, path loss with the help of path loss exponent. So there is a table which shows the path loss effect on this path loss components. The environments is playing the important role to dealing the path loss model uh, in a long distance uh, coverage area. So the table is in between the environment and the path loss exponent. The first column is the environment and the second column is path loss path loss exponent value. This is the table. So the first environment is a free space. The value of n is 2. The second is the urban area. Value is 2.7 to 3.5. And third is shadow. Shadow, urban region. The value of n is 3 to 5. Fourth is in building. With loss. The values is 1.6 to 1.8. Another environment is abstracted buildings, tall buildings. Abstracted building. The value fell and is 4 to 6. There are another environment, abstracted factories. The value fell is 2 to 3. So it is obviously we have seen the environmental exponent values. If we take in free space, that is n is equal to 2. So from this model, we have concluded that the path loss exponent depend on the specific environments. Specific So it is also important to choose the reference value. Do not, that is either 1 kilometer for the outdoor, 1 kilometer for outdoor, and do not, the values is taken 1 meter to 100 meter in is for the indoor. So the main conclusion part is that the path loss exponent will depend on the different specific environment, and the main drawback of the log distance, it is not differentiate between the transmitter or receiver dependent on the separation distance, dependent on the separation distance. But in the formulation, we will include the separation distance only, so it is will be removed this problem in the long normal shadowing. Thank you very much.